first of all, let's get this working, hopefully. All right, yeah, so a little bit about me first, so you know who I am. This is me. I enjoy hiking. That's where the picture's taken about 2 weeks ago. I'm from Denmark originally. I'm currently living in Boston, though one should be careful to call oneself a resident, right? In the US, it's kind of like I should be aware all the time that I'm only there because they allow me to be there, but I'm resident for tax purposes for sure, that they don't mind. I have a PhD in quantum physics from the Niels Bohr Institute in Denmark, did a postdoc at Harvard and later again at University of Copenhagen. Then I've been assistant professor at QTech, TU Delft, also leading their quantum internet division, before I moved to the US in 2023 to take a position at Harvard, jointly in academia and industry, first at AWS, which then we spun out to a company, LightSync, which then got acquired by IonQ. All happened within kind of a year. So a lot of things going on there. That's a little bit about me. Okay, so I'm happy that some of you put Spin-Photon Interface and whatnot. This is what I hope that we will be able to do after this lecture. So one is indeed to discuss the main physical mechanisms for photon-mediated entanglement between individual spin systems. So here I'm already limiting the topic a bit. We're not going to talk about spin squeezing or photonic squeezing or anything like that. CV systems is not going to be part of this lecture. Also not ensemble-based systems. Also not, had to cut it somewhere. And two, that hopefully you'll be able to get some building blocks that allows you to derive and compare different entanglement schemes. Maybe if you want to talk to experimental colleagues or as an experimentalist trying to design the experiment, which kind of photon entanglement schemes should you use? Hopefully you can use some of the things that we're going to talk about today. Okay, so just to motivate a little bit the focus of why I'm going to consider, focus on single spins. So it is something that we've seen some quite remarkable progress recently. There's been results from the Lucan group at Harvard. It's been results from the Delft group, Ronald Hansen, on entanglement distribution. There's from Chris Monroe with ions. So defect centers on top, group 4, and NV centers, ions, and also Jake Kobe, for example, from the University of Illinois, have also done entanglement in telecom with atoms. So, these systems, these platforms, all, fall within the bucket of single spins interacting with photons, basically. And given that, that's what we're gonna focus on. All right, so the topics are basically outlined here. We'll have first dive a little bit into mission-based. Probably that's, I expect, probably quite a large part of you already are familiar with this, but then hopefully you can help me get through it. And then we'll go into scattering-based schemes, which is a bit more like cavity-mediated interactions with these spins. And then finally, we'll have a little bit of a summary of these things. Okay, so mission-based schemes, high level like this, we have a spin that it gets entangled with a photon. And then we send that photon to a mode mixing device, a beam splitter, for example, and we detect it to get entanglement between the spins. All right, so the thing that we're going to go through is the so-called single photon or single click scheme that you might be familiar with, and also the 2 photon/2 click schemes, which are kind of the most commonly used schemes that you see in experiments. And in some of the experimental things that I showed before, this is exactly what they use. And the building blocks that we need to go through is basically one, how do we do the spin-photon interface, the spin-photon entanglement? How do we do the mode mixing? How do we model loss and these kind of things and get the trade-offs between fidelity, loss, and imperfections that we have in these systems? And I should say, even though these schemes are actually well known, right, and they've been demonstrated in quite numerous experiments, we're not going to get to that detail level here, but there's still kind of, when you really dive into the imperfections and the noise that you'll find in the experiments, still things that make sense to actually model that people have not modeled before to get these more finer trade-offs between once you put all the experimental difficulty of control and control fields, synchronization, all these things into account, taking and filtering your driving laser from your signal and all these kind of stuff, all these things start to matter. Okay, so this is the protocol, high level, what I've seen before. Right, so we have Alice and Bob here depicted as NV centers because some of the people that's really been doing a lot with this scheme is in Delft, for example. And Alice and Bob, we now imagine that they have each their NV center. And for now, we're just going to model as basically a 3-level system. As you see up here, so we have 2 stable ground states, 0 and 1, and 1 excited state, E. And we're going to assume that this excited state only decays to the 1 state, which is actually pretty okay assumption. Okay, so we start out by preparing each of these 2 people, Alice and Bob. They prepare their NV in this superposition, where this epsilon is a small number. After that, they excite, because excited fits in 1, goes up to the excited state, it's going to decay and emit a photon. And we're hopefully going to capture that photon and send it to the beam splitter. Once we then get a click in one of the detectors, the other side of the beam splitter, we're going to conclude that these 2 spins are entangled. And that's a little bit what we want to go through now. So I very much enjoy that we don't do everything with slides, and this is where especially those among you that are very familiar with the scheme can help me a lot. So let's see, I think I'll just start with saying, okay, so the initial state that we start with, so this is step 1. This will of course be 1 minus epsilon squared 0, 0. Plus square root 1 minus epsilon squared, epsilon 0, 1, 1, 0, plus epsilon to the 4th power, 1, 1. All right. What will the state be after step 2? Take a minute, just write it down, maybe if you have some piece of paper, and then do someone wants to come and put it on the blackboard. Yeah, I would agree with that. Hope you guys do too, right? Basically just describing that when we were in 1, we got a photon out in that mode. Okay, now in 3, we did say that only a small fraction of the light emitted from the 2 NVs are actually collected. And right now we just have, we have a photon out. Now we need to describe how does that photon go into the collected mode, which actually is not that difficult. We are going to insert a fictitious beam splitter basically to model loss. So that just means that the photon that we now written here comes in at the input port. Here we have an annihilation operator A in describing that mode. And it hits a beam splitter with basically a transmittivity of eta. So it's not a balanced beam splitter, it's not a 50-50, it's asymmetric. And basically this other, as you know, for a beam splitter it has to be unitary. We do have 2 input modes going to 2 output modes. This input mode, it's going to be basically vacuum, because we're not mixing anything, it's just that we have the probability to lose our signal. So the A out is going to be what we actually collect, the transmitted one. B out is what we lose. Okay, and you can write down they're quite different beam splitter transformations. It depends on also the experimental implementation, what kind of material you're actually using to implement your beam splitter with. Do you get phase of ion when you reflect? Do you get a phase of ion, whatnot? You can carry this over to whatever kind of phase you might get in these reflected modes. You just need to keep track of it as you go through your calculations. For simplicity, I'm going to assume a very simple one, which you also can realize explicitly, it's not completely made up, where basically the output modes are related to the input mode in this way. Okay, now when I said that only a small fraction is collected, for example, if we look at NVs, there's actually quite a few different things that factor into play when we say how much light do we collect. So one is the fact that when we excite, it's not all the time that we get a photon out. So this excited state also couples to other states, vibronic states. We can end up having a non-radiative decay. So basically where we go to the excited state, we end up down in one state again, but no photon came out. All right, that's basically one imperfection. We also have the fact that some of these photons are not being emitted on the first excited state and down to the ground state, but there's also, because of these vibrational modes, you can couple to other modes as well, meaning that what you actually emit is both a photon and a phonon. And given that we have a fixed energy between that we have put into the system to go to excited state, that means that when we emit also a photon, the photon is going to have a slightly different frequency than if we go directly to the ground state with a photon. And that's a problem because in the end, we want these photons to interfere at a beam splitter. If they come at different frequencies, they're not going to interfere. We're not going to entanglement. So therefore, there's also something like the zero photon line, which is basically photons emitted without no additional photons, good photons, so to speak, that we can use for entanglement. And for NVs, this is, I think, 4% or something like that. So really a lot of this thing we do not get. We have also just connection into fiber, right? So these NV centers, they're in diamond, they emit out kind of in all directions. We can engineer some nanostructures around them to get them to predominantly emit in one direction in a few modes and then couple those into a fiber, but fiber has a different mode, so it's never perfect. So we're also going to do slide there. Then of course there's transmission to the beam splitter. That might also be in our detectors, might not be perfect. So we don't detect every time. There might be, we can get good detectors that has, about 95% detection efficiency, superconducting and whatnot. You can also have less good detectors with detection efficiency of 50% and whatnot. Okay, so do we really need to model all of that? Not really, because all we care about is just, what is the probability that you get the photon that emitted and detect it. And the nice thing is that if you have a lot of these fictitious beams that we can imagine we put in from each of these loss modes, right? We don't care about what happens to the loss mode. That's we're going to trace out at the end. We just care about what is the probability that we get one photon detected. So we can basically take all these things, just lump it into one thing, which we just call the overall transmission probability from an NV to a detector, and we call that eta. All right, so we just need to insert one beam splitter here, and we just, for now, keep it to be this eta here. Okay, now it's going to be a little bit hairy for you guys, because now you need to, again, help me to insert what happens when we have loss to this state. All right, so what you need to use, of course, is this. So saying that, for example, what does that mean? It means that if I come with one photon from Alice, for example, I'm just gonna, maybe I should write over here. Let's say I had one photon, then that is basically gonna go into something like this. And maybe I should use the notation a little bit different. So let me put it like this. Right, so, yeah.
Some people are not seeing, so
space
here, so if you guys want to come here.
Oh, I'm sorry. I can write it here as well. I'm just going to erase it again. So what I was saying is that if I have a photon from Alice, for example, so this is my 8 in, what the transformation means here is that this is basically going to square root 1 photon, 0 in the loss mode. I'm going to call that E, or maybe L is better. I don't know. You decide. And another probability, I'm going to lose it. So that's basically what this beam splitter does. And this is more or less all you need to know for you to tell me what happens to these terms here. Sorry, I'm going to erase this now. Okay. So I hope, again, I'm going to kick you off with saying the first term here, that I'm very comfortable seeing what happens to that. I had nothing, I cannot lose anything, still nothing in my environment. Now let's take the next term. So now I'm not going to do that one first. Let's take this one. Epsilon squared, epsilon. And then I would like one of you to write what happens to this term here. Here. take a few minutes, see if you can work it out. All right. So let's see, we have, this term is here. Yeah. Yes, indeed, you already noticed, that's good. This term, indeed, I agree. So this is basically that we have the photon surviving. And you've corrected yourself here. Yes, we want to insert here. Let me see if I can fit this. And then you want 0. And we have the same thing down here. So I'm just gonna set that here as well. All right, nice. So now it should be correct, I think. Yep. And now let's add the 2 photon term. So here we have the epsilon squared. And we have the 1, 1. And you guessed it, I would like one of you guys to write the 2 photon term, what that will be. Oh, you got it there, okay. Here you go. Yeah, looks good to me, looks correct. Hope you will agree. And thanks again. Okay, so this is nice. I mean, as you hopefully realized, it is really just kind of linear transformation. We just go from this to another one and multiply the terms, even though it's tensor products. I should say this transformation, of course, goes beyond a single photon, right? So you can, if you have multiple photons inputs, you can use the same transformation to calculate what happens when you have multiple photons that get lost. But it will follow, of course, your intuition. If I get 2 photons, I can have 2 photons getting lost. Well, 1 photon getting lost, 0 photons getting lost. All right. So let's look at this. In the end, we are going to herald on actually detecting a photon, right? Yeah. Yes.
How can I see it?
Well, it's basically just a beam splitter matrix, right? So and you can write it as an operator itself, which is some mixing of the 2 modes. Or you can just write it as a matrix in the basis of the annihilation and creation operators if you want to do. So, I mean, in this case, you would just say, okay, A out, A in is equal to, this can warm up. Can you see what I'm writing actually? Okay. Then you just basically have its squared eta, eta, like this, 1 minus eta, and you have, that should be P out, sorry. Like this, and you have 1 minus eta, eta. It's just a matrix like this. And a matrix you can always express in terms of Pauli matrices, for example. So you can also just write this as another operator if you want. Yep. Yes.
So simple, just a simple fuse with the whole physics itself.
Yes, I mean, well, I don't know how complicated the physics is in some sense, because what we're trying to model is indeed just that a photon comes and either it goes into a loss mode or it continues in the mode that you're going to collect, right? That's basically what we're doing. Then if you go down to the physical level, you say, how can the photon be lost? Well, it could get absorbed by some material. It could get scattered in a direction that does not couple into a fiber, for example, right? The physics of that operation we don't really care about, because I don't care about what happens to the environment that the photon gets absorbed in. You're right that physically, if I absorb something in a material, that the material will get the energy, there will happen something, right? And it will diffuse, maybe it will heat up, whatever. But for wild purpose here, I don't care about that because I'm not interested in what happens to the environment. That's why I'm going to trace over it, basically. I only care about the mode that I detect, and that's very clean. I hope that motivates a bit why it's okay to take this kind of simple approach.
Yeah, because here, like, you only have one loss mode.
That could be, indeed, I could have a collection of a continuum of modes that get lost into.
Why don't you write like 0, 0, 0, 0, 0?
Yes, I could. And indeed, if I cared about what happened to the environment, I would need to do that, but I don't. So a photonic mode I can define in many different ways, right? I can also define, let's see, a photonic mode. Can you see what I'm writing here? No, okay, I'm gonna do different. Let's stop this one. One photon like this, I could say, well, that's actually, you know, some kind of integral over some amplitude and an equation operator in mode X or something like that. The X vacuum mode. I could do that. And now, for example, these X could be different spatial directions that I could loosen into and whatnot. Of course, this would be normalized. But this is fine. I haven't really specified to you what the loss mode is. I'm just saying it's something that is, I don't know, say like this loss, orthogonal to our collected mode. Sorry. So you're absolutely correct. There could be a complicated interaction happening when I lose this photon. Basically, I just don't care.
So this E operator is actually like a basically a thermal projection out of this mode.
Exactly. You can define it as identity minus the collected mode. That's what you get into. So it doesn't have to be one particular mode. Well, it is one mode, but if that mode you can decompose it into many superposition of many different modes in case you need to care about what happens to the environment. But for what we care about, we don't, basically. There are cases actually where you do care about it. Just to give one example, this one photon scheme was done with at the Hansen group while I was in Delft there as well, and I talked about this zero photon line, right? That some of these photons they actually get emitted with different frequencies. So either you just treat it as a loss and you just don't care about that information, but what they actually did have an opportunity to do was also to isolate that light and look at that. So in that case, we did care about at least one of the loss modes, which was the light that went in and got collected, not from the zero photon line, but from like this phononic bath modes. The reason why you cared about it was because information about whether you got light there or not could tell you something about the probability of two photon emissions and whatnot from these NVs. So sometimes it is actually valuable to look at these loss modes. For now, in this case, we don't care about it. And you can get around without it, basically. But sometimes it becomes, you can get better results if you do care about it. All right. Okay, back to the loss modes. So I basically argued now that I don't care about the loss modes, which means that I'm going to trace over them, right? Meaning trace out the environment, not assuming that I have any information about what went on there. So if I do that, we should notice two things. So we will have coherence between modes that are the same in the loss space, right? So this has vacuum, this has vacuum, this has vacuum, and this is vacuum. Let's see, do we have another color pen? Actually, yes, a green one here. So that means when I trace over the vacuum, I'm gonna get coherence between this term, this term, this term, and that term, right? Now, sorry? Oh, sorry. Yeah, this is the wrong one. Yes, you're right. It's this one. Yep. And these modes all something where I have vacuum in my loss, right? Then there are modes where I have something lost to my loss mode. I have this one, and I have that one, this, and that. In principle, sorry, I don't know what's going on with this mic. I'm going to put it down a little bit. Let's see if that helps. One thing to note is that I will no longer have coherence between these two terms, right? Because they have different loss modes. One has a in the mode from Bob, the other one from Alice. I think this doesn't work. So coherence here, I cannot get entanglement from these tones, basically. In order to get entanglement, I do need to have coherence between these spins. So any from these things that's lost, I can't get entanglement. The last thing is also they don't have any photon in the connected mode, so I'm also not going to get a click from these. So wait, right? Well, I could protect and say, okay, if I lost it, yeah, I know it was unsuccessful, won't have entanglement. Down here, it is same thing this one, right? That will never need to click. I can herald it away. This, however, and that one, I still have one photon left in my signal mode. I will, however, also lose coherence between these guys, right? Because the loss mode is different. So these will not lead to entanglement between my spins. But I will not be able to route them away because all information I will have access to at the end of the day is, did my detector click or didn't it? So let's take and circle the bad terms here in some sense that I cannot really distinguish them. So this term, I have no way to distinguish from the good terms where I didn't lose the photons. So there's this term here. No, sorry, where is it? Here. That's in principle also bad. I'm keeping it as green for now, but actually this is bad because I have two photons. I basically just get a product state of my spins on one. Right? But I can also, in principle, not distinguish this. Well, I could because I have two photons in a single mode, so I will get actually two photons detections at my detectors. And here comes in the experimental lab, how good they are. Can they resolve those two photons or can they not? Right? Do you have number resolving detectors or don't you? If you don't, then you cannot distinguish this and it will be basically an unheralded error. If you can, then you could distinguish this. If you can actually distinguish between getting one or two photons on your detectors, then in principle you could distinguish this and you can throw it away. So I think we should be nice to the experimentalists and say you don't need to have number resolving detectors and whatnot. We just assume that you cannot distinguish this guy and keep it. Okay, so let's get to the final point, which is after detection, we should have entanglement, right? So the green terms are the terms that I get when I detect a photon. These terms that I have not done anything to, those will be able to route away. So they will just go into a success probability. Okay? Let's look at the good terms. And also, as I mentioned, this actually will not lead to entanglement. Okay? So to see what happens in step 4, when we do this final detection, let's go, whoops, back here. Well, we do the combined B stutter. We maybe should get to that first. So let me focus on this part. This is actually the interesting part. These terms here. So now we have, switch back to blue. Zero, 1. And actually, let me write it a little bit differently. So we put the square root of eta. And now I've traced over the vacuum. It's just 0, 0. I forget about it for this. So we just have basically this term, 0, 1 photon plus no, 0, 1, 0, 1 photon plus 1, 0, 1, 0 photon. Now I'd like to see what happens when I go for a balanced beam splitter with this guy. And you don't need to calculate that. I'll give you the answer. But the approach is exactly the same as you did with loss. Right now, just eta would be 1/2. So I can just insert that. And what I'll get is that the beam splitter in the middle here will transform this into 1 minus eta squared, eta this, and we'll get 0, 1 plus 1, 0. Square root of 2. Zero. So I've just taken the photons here and transformed like in the beam splitter with loss, just putting 1/2 as the loss. And now these modes are now really the detected modes. So these are the modes after the 50-50 beam splitter at the middle. So add the two detectors. And you can see if I get a click from these terms, I'll prepare an entangled state between my spins. Right? Do you agree? Good. Okay. Now I know the good term, that works, gives me entanglement. Unfortunately, I'm a little bit short on space here, but let's see if we can fit it in here. We're going to write in this little slimmer here. Okay, so the probability that I get entanglement, you should be able to get from what I wrote here. So what is the probability that I get entanglement? That's right. So that's 1 minus epsilon squared, eta, basically. Yeah.
Before the beam splitter that one of the detectors will play.
Oh, sorry?
Yeah, you have put condition before the beam applying beam splitter.
Yes.
One of the detector plays.
No. Well, by singling out this term, I said, let me just focus on that term because that's the only term that can lead to a detection. The beam splitter transformation is independent on whether the photon is going to be detected or not. I'm just applying it to the terms that I wrote here.
But we trace on these terms that we have condition on the.
Right, that's because before we did loss, so the loss mode we didn't detect, we just traced over it. In this beam splitter, we have 2 input modes and we have 2 output modes, and we're going to detect both modes. So now I transfer them into just 2 detection modes, not 1 detection mode, 1 loss mode.
But usually, like we think if we are applying trace, that means we are detecting that thing, and then it's being traced out of the system.
Yes. So I haven't detected yet. This is how the state looks like before the detection. When I detect, I'm going to project onto either that one or that one. Right? So the detector is going to measure whether detector left or detector right clicked. That's going to project onto one of these.
Before we have to trace on condition number 3.
Yes. Yes, I haven't traced. Yes, indeed. So because I didn't want to go through and write a big density matrix, I've kind of said, okay, I can split when I do the trace. I know that I'm going to get, basically a statistical mixture, which is a density matrix, between different things that can happen. One, no photon in the environment, right? That would be that I have this term, this term, this term, and this term. So I could continue my calculation just with those terms and say that is what happened when there's no photon in the environment. Then I can take separately, this is what you do in a density matrix, right? And say, okay, what if I detected one photon in the loss mode of Bob? I can take those terms and see what I had got from those. But what I can see already now is that, at least for these guys, I will never have a signal photon. So they will never be able to lead to a click. We'll get back to what I'm neglecting here, but we'll never get to a click. So I don't really want to take these further in the calculation. I'm just saying I don't care what happens to them because I know that I'm going to herald them away anyway. The only thing that I need to treat a bit more carefully is this one, because this I cannot herald away, as well as this one, because that I also cannot herald away. However, this here, when I trace off the environment, I can treat these separately, right? Because this is like one loss mode in loss Alice, one in one B. So I can also just look at what happens to those terms completely independent of the others and just sum them in a density matrix with the right probability. Yeah. So I also, we're doing a little bit fast here in some sense, and I do definitely recommend that you can start from this and you can go through the whole thing, just write it down and do the trace and you'll see the density matrix. Please do that. That's also good to make sure that I didn't make any errors when I do this. I'm doing a little bit fast here, but in principle, what you should get to is indeed, well, we can just focus on the terms that we know will give it a signal and derive, because in the end, what I'm after here is I want the success probability and I want the fidelity when we get a click. And that's where we're heading. So now we have the success probability of this guy. So that is the one that gives us an entangled state. Now, sorry, that's the probability that we have a good entangled state, is this guy. But the success probability, which I define as basically the probability that I get a click, that's a different beast, right? So naturally it has also this term. Because that's the one that we could get up here. But there are other terms that can lead to a click, right? So which terms are those? It's this term, and it is these terms. They can lead to clicks. Do they lead to entanglement? No. Right? Because this is a product state. There's no coherence between these guys because I'm going to trace over the loss. So these are not going to give me any entanglement. And now I'm just after a little bit kind of a lower bound on the entanglement I can get. Right? So I know I have great fit entanglement if I get this term. Now I want to add to the total success probability. This was the good term. What's the probability that I get bad clicks, so to speak, clicks that doesn't lead to entanglement? Epsilon 4, epsilon squared, right? And there are two more terms that leads to a click. That's right. So 2 epsilon, 1 minus epsilon times epsilon, sorry, eta, maybe, times epsilon to the fourth. Okay. Right, so this is the probability that I get a click from that guy. And again, I didn't care about going through the beam splitter transformation. In principle, I should do that for this photon as well, right? I mean, these two photons, they come on the beam splitter, and actually now we can't just do this. We do need to go back to this guy because we have two photons. They could bunch and all these kind of things, Hongo-Mandel and whatnot. You can go through that definitely, and I encourage you to do so. It's a nice way to also treat the beam splitter with more than one photon input. But in the end, I didn't want to do it because I know that I still don't get entanglement from this term. For now. Same with these guys. In principle, I should go for the beam splitter and derive, but I don't care, basically. And that's because what I want is basically just a lower bound on the fidelity of the entanglement that I can get. Right. And I think when I detect, I will have no coherence between this term and either of these terms, right? It will really be like separate probabilistic events. Just as you would imagine, okay, I detect two photons, I get that state. I get one photon on the environment, I get that state. The only one that I need to care about coherence between the terms is this part, basically. Okay, so how do I get a lower bound for the entanglement in the system? So here the entanglement you can measure it in like the fidelity of the bell pair, right? So in this case, of course, note there is a phase difference between these two, right? But I do have the classic information about which of these I'm in. So therefore, I can always do a correction of the phase if I wanted to have the same bell pair every time. So therefore, I'm just grouping these, right? And saying whether the left or the right detector crits, I still have perfect entanglement. That's this term. Then I have the total success probability. How do I get a lower bound on the fidelity of my entangled state? This has fidelity 1 with the bell state. These guys, they'll have some fidelity, some overlap, right? We're still in the computational space, even though I have a product state 1, 0, still have overlap with a bell pair, right? 50%. I don't care about that. I would just want a lower bound. What would be a nice, easy lower bound for the fidelity of the bell state from just my success probabilities? Think of it as really classically what can happen. With some probability, you get a state with fidelity 1. With some other probabilities, you get states with, let's just assume fidelity 0. Then that definitely gives me a lower bound. So the fidelity would basically just see, well, what is the ratio? Yes. P happy, PS. And I should say, is this a lower bound? Because some of the states that I get, even though I get a click, still have some overlap. So it will be a little higher. But given that I want fidelity 95%, I don't really care about that. Is it clear, this bound? Okay. So let's see, did I derive it correctly? I hope so. Yeah. So that's our fidelity lower bound, that's our success probability. And here is why we want epsilon to be small. Well, if epsilon is not small, we're going to be dominated by this guy and no entanglement, right? And these guys, they scale also with this epsilon. So I will basically not be able to herald away my error in the presence of loss, even though I have not resolved the detectors or not. That's why I want to keep epsilon small. You see the success probability now scales with this epsilon and the transmission. Transmission, just one photon, it's just eta. My fidelity scales as 2 eta epsilon squared. So by tuning my epsilon, I'm making a fundamental trade-off between my success probability and my fidelity. And that's a little bit kind of the curse of the single photon scheme. That in order to have really good fidelity, my rate is going to go down because many times I'm just not going to get, a click pattern that leads to entanglement. I basically won't get a click. That's the point. Okay. So that's like the, I think, first order imperfection that we have. But there's a lot of imperfections here that we didn't include. And let me see, I think it's a 2-hour thing we have, and now it's 10. So I think now is a good time to take a little bit of a break, like 10 minutes or so. And when that break, you should of course relax, but also think about what imperfections, especially the experimentalist, I think there was 11 of you, in the, should come back and tell me, this is all nice, it's still theory, it's still, not exactly what goes on in the experiment. There are a lot of things here that you're not taking into account. I would love to get input on what those things are. So take 10 minutes now. Think about that. And then I guess, okay, maybe not 10. 10 minutes past 10, we are going to start again. We'll start again. We'll start with a few corrections. Always typos sneak in. First and very most important correction, thanks to you. I don't remember your name and you're looking at your phone, but thanks to you. Typo, there should of course be a 1 minus here. Fidelity is improving as we decrease epsilon. It's not getting worse. Second thing, which is a bit more, not so much of a typo, it's more as a not super being very careful here. Success probability, it is of course this, which is the full success probability. What I wrote up here is just the leading term. right? Because the other terms are to Epstein fourth, so I kind of just bit them out. But the full sequentiality would be exactly this that you have here. Okay. Whoops. Oh, you're not supposed to see that table yet. Sorry about that. So let's. I hope you had some time to think about imperfections that we didn't include. So shoot. Especially experimentalists among you. What did I forget here? Yeah.
Everything is too symmetrical. For example, the losses, less probability of exciting. So I don't know if you think the distance, this is different.
Yeah, I very much agree. That's usually not the case, that they are exactly balanced, these things. We might have different laws between these two. We might have a different optical phase. So let's put, what should we say, anti-symmetric conditions, laws, optical path. Especially since these NVs, they're implanted somewhere in this diamond, right? And they might be emitting from different locations and whatnot. And so what would the effect be? Well, loss that's imbalanced, we will actually also get a not, it will hit us fidelity, right? Because when we now detect a photon, there will be probably a higher probability the photon came from one Alice than from Bob, if we assume that, for example, Alice has a lower loss than Bob. So that would be an imperfection, phased optical path. Here I just assume that both photons from Alice and Bob, they were completely the same all the way through in transmission. Of course, when a photon travels, it does pick up phase. If that phase is not the same, I cannot just assume these to be just these two states. I will need to keep the relative phase between them. That relative phase would turn out in my Bell state as well. So if I know it, that's great, it doesn't matter, just correct it. If I don't know it, then that will also limit my fidelity. So phase stabilization is something you also need to do in the single photon scheme here. That's actually very important.
Assume the NV centers are indistinguishable.
Exactly, yeah. And that can also, let's put it here as well. I'm assuming that there's exactly the same frequency that these two emits and whatnot, and they will not have. So there will be, again, slightly small different frequency differences. These photons are not completely indistinguishable. That will limit my fidelity again. Exactly. They emit at different times. That can also limit my fidelity. Yeah. Sorry? Dark counter detectors? Yes. So even though there was no photon, my detector clicks. Actually, how to model that would be to take your beam state transformation, and instead of putting a vacuum in, you put a thermal state in. And then you can model also dark counting the effect of those. So first order, you can also just say, with some probability, when there's vacuum, I get a click. It will get exactly the same thing. So if you want to keep it simple, you don't need to put thermal states in. Other things? Yeah.
So at the beginning of this extent, maybe this extent using photon quantitative pathway.
Yeah, so you're saying an excitation pulse, that this is not perfect, and it could lead to what, sorry? Or
So after you excited, when you did
decays?
relax,
Yeah.
maybe, so we suppose that it emits a photon, but
Yeah.
maybe it can relax more aggressively.
Yes, that's true. That we actually did take into account, because that would just factor into our loss in some sense. But another thing that comes from this excitation pulse is also double excitations. Or you say two photon emissions. Because our excitation pulse is finite width in time, right? So it's not like a instantaneous thing that bring it up. So what can happen, as soon as we're up there, we can start to decay, right? So when we're in excited state, then there's, time, and we start up in the excited state, then we're gonna have, exponential decay. So even at very short times, there's a probability that I actually emit a photon. Even times, especially if my driving pulse, my exciting pulse is now long, it has a certain time. Let's say that this is the window of my pulse that tries to bring it up, right? So I have something that brings it up, and I have soon it up, and something that decays. There's a non-zero probability that it decays and then gets excited again, and then decays again. And now there will be two photons coming out, and most likely I'll lose one of them, and that tells immediately that, hey, this NV was in the bright state, in the one state, so no entanglement. Kind of the same effect that, if this two photon term that we looked at. So these double excitations, also a problem, and there is really, to model that, you need to look at what is the width of your pulse, right, compared to your decay rate of your emitter. And sorry, just one thing there is now, if an NV is in a bulk diamond, it has a certain decay rate. If you go to some other defect centers like group 4, it can be in cavities. Cavities enhance your decay rate, so it's even faster. Meaning that if we can go into a cavity and we get better photon collection, but now something like this, for example, we need to be careful because now we need even shorter pulses not to have two photon contributions coming out. What you can do, which they also do actually, is that you can start to do some time filtering and say, okay, when I do the detection here, I have photons that are very close, so I limit the probability that two photons got emitted. Then you run into trouble with, I still need to distinguish from my driving pulse, and if that's the same frequency, how do I do that, and whatnot. So that's why I start by saying that when you start to dive into these things, there are actually some non-trivial kind of trade-offs that you need to put into modeling and do in theory to can actually help guide the apprentice to get the best results, even though these are schemes that have been known for 25 years. You wanna?
Well, time synchronization.
Yes, so we're assuming that these two NV centers are living in kind of the same frame, so to speak. So we have synchronization between operations on them that we can say, now you both emit, we drive them up and whatnot, indeed, and we need to ensure that. So, of course, we can do that by classical means, but yes, indeed, you need to do that too. So now I wanted to put this in here. This is actually from this paper. And this is from an NV experiment. It's a 3-node experiment, but here they're just looking at doing entanglement between node A and B or between B and C, and they're doing the single click scheme. The centers, this is from the Hansen group. This is not so much. Well, you can see here that they indeed do have different detection probabilities from two links, but they've been linked to be the same, so that's why the infidelity is not affected. But if you go down here, we have that these anti-symmetric kind of things comes in, right? That these alpha 1 and alpha 2, here alpha 1 and alpha 2 is what I call epsilon. So this would be epsilon 1 and epsilon 2. They're actually not quite the same. That leads to an infidelity because there's now more probabilities you get a photon from one than the other. There's dark counts that we discussed. Visibility between the photons and discredibility. Optical path, these NV centers are not the same. That basically goes into this visibility, right? That these two photons are indistinguishable. And therefore, when they interfere, you don't get perfect visibility in the bell curve. And you can see the kind of all at that's actually, let's see, at percent level, right? So kind of a couple of percent actually, not so good. Double excitation, actually also kind of large. So that's also a limitation here. So these things really matter. And that's where, going a bit more, if you really want high fidelity, you need to incorporate those in your modeling as well. So the thing that we did now is great. It gives you the kind of fundamental trade-off between fidelity and rate in a sync-photon scheme. That will give you an order of magnitude, well, better than an order of magnitude, but all these things you need to include in actual experiments to capture what's happening. All right. Whoops. Pause here for questions for the sync-photon scheme. Otherwise, we'll continue with the two-photon scheme. All right. Yeah, sorry. Yes, also the photon doesn't really dephase, so this is just a single photon traveling, right? But you can say one of the things that we discussed was it can pick up a different phase depending on the optical path that you have. That leads to a dephasing of the entanglement, because now these two photons are no longer, I mean, when you get the click, you'll get an entangled state with a phase that depends on the relative phase difference between whether a photon came from Bob or whether a photon came from Alice. And if you don't have control of that phase, yeah, you're going to effectively dephase your entangled state, because you're doing an averaging now over many different realizations where this phase is maybe fluctuating, and that leads to a dephasing. So indeed, for experimental demonstrations, and also in this paper that we looked at, they have done active phase stabilization of the path, meaning that they're tracking the phase. So you send basically a classical reference and check what the phase is, so that you know what it is, so you can get rid of that. But indeed, that's also another kind of good thing to keep in mind about the single photon scheme. You do need phase stabilization. And actually, for what we're going to discuss now, that can be significantly relaxed for the two photon scheme. All right, so two photon scheme is exactly the same setup. Only thing is, I'm now assuming that I can do some more things. So I will no longer prepare it in like this asymmetric superposition. I'm going to prepare it in an equal superposition, which is 0 and 1. It's exactly the same state. If I'm in 1, I'm going to excite to E and decay, just as before. Then after I've excited, I'm going to do rotation, of basically going to flip them. And then I go back and excite again. And then these photons I'm going to collect on a beam splitter and do detection. And if I detect an early and a late photon, my claim is that I have entanglement. So I need to detect two photons, one from the early time, which is the initial, the first excitation, and one from the late excitation. Note that one single NV cannot emit both, right? Because either it is in the 0 state or in the 1 state. If it's in the 0 state, it's going to emit in the late time bin to begin. If it's in the 1 state to begin with, it's going to emit in the early time bin. So the only way that I can get a click in the early and in the late is if one NV emitted in the early and the other one emitted in the late. And the idea of the beam splitter is to erase which one emitted what. And that's how I get the entanglement, high level. Oops. Okay. Okay, so I think we're gonna, yeah, let's see, go a little bit through this, but we don't need to do that, carefully as we did before, because many of the things are very much the same, right? You have laws, you model it exactly the same way. The beam splitter transformation is exactly the same, but let's just maybe, yeah, let's go back so you can see the protocol. And naturally, the initial state is very simple, right? It's just 0, 0, plus 0, 1, 1, 0. And now, let's say step 3. I'm going to skip step 2, just go right to step 3. And let's use the notation that we have 1, 0 early, or 1, 0 late. This means a photon from Alice's side in the early bin and nothing in the late, or else a photon from Alice in the late time bin and nothing in Bob's side. So for Bob, it would be 0, 1, E, and 0, 1, late. Right? So these are the different photon emissions we can get. Of course, we can also get 2 photons in the early. Something like 1, 1 early, 1, 1 late. So these are my photonic modes. Now I've chosen the notation. Now I'd like one of you to write what the state looks like. Forget about loss, just what it looks like after step 3, when I've done these excitation, flip, excitation. Keep in mind the flip in between. So take a few minutes and see if you can write this down. Yes, now I just want you to write it out what happens like early and late, this notation that I have here. No loss, no anything, just kind of how it would look like if I did this perfectly and I got these photons out. So 3. And as before, once you got it, please come up and write it.
When the game happens, why does it go always to 1 and 0 instead of 1?
Oh, right, selective, right, indeed. So this is due to selection rules basically inside the defect center. So whether you actually do have a single photon coupling between 0 and E. And you can have, you can have very high degree of suppression of any, basically a very, very weak transition, because it's more or less forbidden to go from 0 to E, meaning that the probability of doing that is very, very small. But it varies from system to system, right? And especially if you're working with atoms, who's also doing this and whatnot, has a much richer level structure, and there you need to carefully look at your Klipsch-Gordon coefficients, whether can I make these kind of isolated optical positions or not. Yep. Oh, just get it without the cap. Yeah. Awesome. And you correctly flipped the states, which is nice. That's always where I forget that you actually flip them. But yeah, exactly. So if we end up in 1-1, meaning we started out in 0-0 and we emit 2 in the late time bin, or these cross terms, and these are the intersection terms, right, where we get 1 early and 1 late from either Alice and Bob. And we have this term where we get 2 earlies. So in some sense, we're almost done. Right? Because, okay, we can now put loss in, as we did with the single photon scheme. We can lose photons from that guy, we can lose photons from that guy, and we can lose photons from this guy. If we lose just 1 photon, I can herald it away. Right? Because what I'm saying is that I only take it as a success if I detect 1 early and 1 late photon. This one I will never get success from because I have no one in the early. So I'm already going to throw that away, right? From my post-selection. Same with this guy, because I only can get clicks from the early bin and not the late. So those I will never herald. These guys, if I have any photon loss, I'm also going to throw them away. So I can go through the loss. I don't care about it, because what I can say in the end is the only thing I'm going to have success from is these two states, and my success probability is basically going to be eta squared, or times. Now I should not write the success probability, I'm just going to write the state. So I'm going to have, with eta squared, I'm going to have exactly this state. All right, so here I've just taken loss. What does that do? Well, it means that the only thing I need to care about is now this term here. I have not normalized it yet, right? Because in the end I want success probability. But this is the only thing surviving after the loss that will lead to a success. Everything else will just go into non-success. Right? Nice. Okay. What does the final beam splitter do? It mixes these exactly as you did before. You basically means that if I had a 0, 1 E, it's going to become a superposition between 0, 1 plus 1, 0 E. It's mixing whether I got the photon from Alice or from Bob. And of course, then, depending on whether it's the left or the right detector that clicks, I'm going to get a phase in the bell pair that I'm creating, but I'm going to get a bell pair. If I herald, I'm getting one late and one early. So, in the end, I should have this, sorry, because it was square root of eta. This is going to be my state. Perfect bell pair. Because I'm heralding everything away. The bad emissions, the loss. But my success probability is going to take a hit compared to the single photon scheme. So, why isn't this there? Yes. So in the end, my success probability is going to be 1/2 eta squared. So I need both photons to survive. The single photon scheme, it only scaled as eta. So if I have a lot of loss, like for an NV, I start with 4%, just getting out. There's a big difference between eta squared and eta. So that's why in many of the Delft experiments, they use the single photon scheme. Because otherwise their rate is going to be terrible. And well, you need statistics enough to do the experiment. And it's not nice to keep everything stable for a month to take data. Right? So that's why you do something like that. For this one, very simple calculation, the fidelity is 1, right? Because as soon as I get this click, I have a bell state. There's no terms that can lead to a click pattern that I take as a success without this. Yeah. So I have, you can think of it as 2 terms here with 1/2 each. So that's 1, 4, 1, 4. So it gets 1/2. Yeah.
Apply the spin rotation. You apply magnetic field.
Well, no, sorry. The spin rotation don't apply magnetic field. You apply like a microwave field to do. A microwave field. So you have a magnetic field on, basically to define your qubit and your quantization axis. And then you put a microwave drive basically to drive your spins. In the NV case. I mean, with atoms, you can also do it with optical Raman and about, yeah.
With this was you also assume that the individual states basically the generation of containment and that will lead the.
You're actually correct. And if you're talking about long distance entanglement, that starts to be really a bit of a problem, right? That if we actually need to wait until the photon arrives, get a click and send back, then you could in principle have a problem. If your continuous time is good, should be okay. For these NV centers, it can be quite good. For other things like group 4, for example, they need to cool down to get good coherence time, or use nuclear spins to do it. But yeah, Yes, okay. Those like an internal coherence time of your spin in itself, and here, I mean, in this, I've just assumed it to not matter. Yep.
How do you differentiate the two earlies arriving at different times and one early and one late?
Right. So
Guarantee that the centers actually meet at the same time.
no, but I can time my experiment basically. So I say in this time window, that's where I do my excitation pulse and wait until a photon can get out or not get out. Then I'm gonna, at this time, do my spin rotation, and then at this time, I'm gonna do another excitation. In principle, I can put these as far from each other that I want. What my coherence time of my spin is, of course, but I can control the early and late time bin window myself, how far they're apart, right? So you can say in time, you have the late window here, and you have the early window here, and this guy, that's something that I experimentally can control.
If the experiment is really like bad, you have to like make this time period much longer and then stable here.
Yes, so you're gonna have, so what determines this is, you know, some limitations of this. What I'm writing here is kind of the distribution of emissions times when I do my excitation, right? It's not going to be at one fixed time, it's going to be some distribution over this. And I want that distribution to be the same for the two NBs to get interscrutable photons. And what I want is to make sure that I now time my experiment such that these are well separated, such that I really have a good early and late time bin. In the end, you can say, what I want is that early and late are non-overlapping. If I put them too close together, they will be overlapping in some sense, right? And then, yeah. And if you can't control this, you can also control your detection. You can also say, I just only accept photons that are emitted here and only accept photons that are emitted there. That's another way you can control this delta T. So it's kind of, it will indeed, if your distribution of photon emissions is broader than your acceptance time window, then you're gonna hit it go into eta, basically. Because then there'll just be photons you don't detect. All right, so high level, two photon scheme, better fidelity than single photon scheme, not so good rate. I mean, we also have the epsilon in the single photon scheme, so it's a bit of a trade-off, kind of, you know, how big an epsilon do you want, what kind of infidelity do you want, do you win? Of course, you can always say if eta is really, really low, you always have a better rate in the single photon scheme for all practical affinities. But this thing that affinity is high, meaning that if we have something where we don't have a lot of loss, for example, maybe you want to do the two photon scheme. Fidelity is of course not one, right? So what information didn't we include? Well, many of them are the same as we had before, right? Dark counts, yes, that's something we didn't encounter. I mean, this is for the single photon scheme, but dark counts, so don't take these numbers. This is not the experiment, but these same things will be there. The dark count rate will be there. The visibility will be there. However, let's think about a little bit this optical phase stabilization. So for the single photon scheme, I really cared about this phase to be stable over each realization of the experiment, right? Because if I had a different phase from the two photons, I end up with a different bell pair. In this scheme, if I put in a relative phase between photon from Alice and photon from Bob, you should try and go through the mass to see where does that phase end up in your final state. Because remember, we are always taking a photon both from Alice and from Bob that goes into entangled state. And I'm not going to go through it now, but basically what you'll figure out, hopefully, is that your phase stabilization now matters only on the time scale of the early and late. So you need the phase to be stable between early and late, but you don't need it to be stable across the different realizations, as in the single photon scheme. So your phase stabilization requirement is much relaxed in the two photon scheme compared to single photon scheme. This is another thing that makes sense to weigh in if you do long distance things, or from a satellite to ground, for example, where it's difficult to keep things phase stable, their two photon scheme might also be better. right? The way to think of it is that the only way I lead to success is that I had a photon both from Alice and from Bob. So a relative phase just becomes a global phase. Except if I have something phase difference between the early and late time in. Okay. These things don't matter anymore, of course. Epsilon is not no longer there, so that will not be there. Double excitation probability will also be there, because we're doing the same thing. We're doing a short excitation pulse and let it emit. So we can still, again, there have that we emit 2 photons, one of them is lost, we lose the coherence, but we don't detect it. So all these things will also matter for the 2 photon schemes. They will never have fidelity 1, but because you have this fundamental difference between that and a single photon scheme, in many cases you can get higher fidelity at the expense of a lower rate. Any input on imperfections that I might not have included or discussed so far?
It's quite interesting that the total error is like basically the same as the other, so you get.
Well, yeah, sorry, that was this is not for the 2 photon scheme. Sorry, this was actually just to say that, okay, these things that have the single photon scheme, they're the same for the 2 photon scheme. It's not the same experiment. So yeah, that's why there's a very big correspondence between the errors here and the single scheme. I looked very hard to get like a good paper that did 2 photon scheme with a nice error table. Unfortunately, I couldn't find it. They all discussed the errors in depth and length, and had I had more time, I tabled myself, but I didn't have the time. So yeah, but maybe suggestion to experimentalists in the crowd is really nice if you put an error table like this in your paper. It helps a lot for theorists to figure out, okay, what is actually these things, and don't need to dig through supplementary material, section 1, 2, 3, 4, 5 to figure out all these things. All right. Let's see. Whoops. Sorry, just acting up a bit. Okay, so let's wrap up here with a few questions for you guys. This is the emission-based schemes. We talked about the single photon and 2 photon schemes. We talked about imperfections and what they do and what not. One question, and I mean, it's not a super easy question, and so just throw something out there. If you were either an experimentalist that need to design your system, and if you are, keep in mind what hardware you're actually using, or if you're a theorist that need to give input to an experimental group, like, I think you should do this scheme, what factors would you take into account to see which scheme would you go for? Single click scheme or the 2-click scheme? Yeah. So fidelity and distance or rate, I guess, is, yeah. And so just writing down here. Question 1, target fidelity. What could set good target fidelity? What's a good target fidelity? Yeah. Error correction, you say?
It depends on the which kind of error correction or resolution protocol you want to use.
Yeah. Error mitigation, correction. Do you have that? I guess what you're saying is like, do you have some extra techniques that you can use to boost the fidelity, for example, from what the single or 2-click that can motivate whether you want to go for the single click with high rate, slightly worse fidelity, but you can then boost it, for example. It actually goes a little bit to question 2. So we have that there. What would be a good target fidelity? I'm just going to ask the question. Like, where do we want to be? You're going to get 1. So,
Is it like any scheme, is like threshold, right? Like, if I work above this, I don't know the schemes.
Didn't you have someone talking about QKD and whatnot as well? Is there a threshold for that? yes, the qubit error rate goes into fidelity in some sense. If it's a bell pair, kind of, they're two sides of the same coin. So you can also say, if I want to be able to distill key, for example, right, application QKD, look, I need fidelity higher than 80%, I think, something like that, 78 or something like that, I can't remember. Otherwise, it just can't distill key. Okay, so I definitely want a fidelity higher than that. Could also be that it's a barrel inequality that I want to show. Okay, then 80% is not enough. I need to do more, maybe not 90%, right? So indeed, what motivates your choice? Well, actually, it's also a little bit like the application. Sometimes the experiment, you don't care about the application, you just care about the demonstrations. It could also be, well, nobody entangled these systems before. I just want to show I want to have an entanglement, something non-classical, I want fidelity higher than 50%. For example, if you look at many of the papers in the beginning, like these networks that were deployed, the fidelity is sometimes just above 50%. Sometimes it's 70%. That's where it doesn't really care about the application. It's just more demonstrating, hey, we entangled nodes over a network, right? We did some non-classical things. So these things factor in what you actually want to do, and then the rate. And rate, of course, you can also say application. Another very big one is exponential time it takes to acquire, statistics. If the rate is too low, you just won't be able to, run the experiment long enough to get good data, and then you can't do it. So that will definitely also play a role, and also was one of the motivations for example, depth experiments and whatnot for single click stuff to play. Okay. So back to your thing about error correction and mitigation. So how could you address the fidelity of the single click scheme? Error correction, detection, purification, and I'm just going to put here, look up extreme loss protocol. This is a purification scheme, so you need two pairs, but because we know in the single click scheme what the infidelity comes from, it comes from this 1-1 state. With two pairs, you can basically completely correct that. So you start with two pairs that has very bad fidelity, but with a single purification, you get perfect fidelity. Well, okay, very good fidelity by doing purification. So in principle, you can do that at your expense that you need now to keep two bell pairs, have them present at the same point in time. If one decoheres while you wait for the other, then that's going to be a problem. If your phase is not stable on this isotope, that's going to be a problem. And for example, atomic platforms, that's a bit of an issue. If you really start diving into details, you can also say if you have an atom, for example, trapped with an optical tweeze or something like that, and emits a photon, when you emit something, you're going to get a momentum kick. That's also going to play a role, right? Because it means that now these, depending on when you emit this photon, you will have different phase accumulation of these atoms. And that's, I think, one of the reasons why, for example, that no one has really done this single click scheme with atoms or ions in these traps. If you're interested in that, I think David Nadlinger from Oxford, he actually did some very nice kind of theory work on modeling these phase kicks and how you can mitigate them potentially and whatnot. And I think they also work on trying to implement the single click scheme. But just to show again that, yes, these are old schemes, been around for centuries. Well, not really, but 25 years, something like that. But there's still ongoing experiments on trying to understand the more details of it, depending on your hardware model. Okay, another thing is, the photonic qubit we have so far, the single click scheme, it was what you would call like Fock space encoding. There's a photon and there's no photon. In the two-click scheme, it was a time bin, early or late. Are there other photonic encodings we could get work with these schemes? In particular, for example, the two-click scheme. Yeah. Exactly, yeah. Polarization encoding, exactly. Many have done the two-photonic scheme with polarization encoding. So this is not where we do like this emission, flip, and emission. This is basically where you say, I excite to excited state, and that can go down to 0, or it can go down to 1. But these have different polarizations. And then what I'm heralding on is not to get an early and a late photon, but get one polarization photon and the other polarization photon in the detection. So many experiments have done that, indeed. In general, there are quite a few different things. You can also do it with frequency. So it could also be that these 0 and 1 are not degenerate in frequency, but two different frequencies, and now you want to detect the photon on one frequency and detect on another frequency. You could do that as well. Dual rail is kind of time-benders. Also dual rail is just this is in space. You could say, okay, one I emit in one direction, one in another direction. Just to say that actually these entanglement schemes, it doesn't have to be the way I describe it now with time and whatnot. You can also go through kind of for the same similarity, similar scheme, slight differences, but with different encodings. And depending on your hardware, yeah, atom ions, they've done it with polarization. They could also do it with time bin, and then they're also looking to doing that, I know, some of them, but again, it just depends on what is the most easy thing to do with your system, given your level structure, which is not just going to be 3 levels, but for atoms, 25 levels or whatever. Yeah.
I guess one thing to point out as well is that you can convert between these encodings, right? Like setting up polarization, then you can put PBS to rail, so
yes,
mix and match different systems are naturally converting to these encodings, but to some degree you can mix and match.
That's right. That's right. There are methods to go through all of these, and as you say, it can be varying from, for example, if I want to go for polarization to do a rail, it's just a polarizing beam splitter. I put like one polarization in one arm and the other one in the other arm. That's very easy. Going to time-bend polarization, that's a bit more difficult. I need now to put these photons into the same point in time and with different frequencies, but there are ways to do it, indeed. And you might say that you need to start with one encoding due to your quantum system, maybe polarization. But now if you want to send that over a long distance, you need polarization preserving fiber. That's expensive. Maybe you want to translate that into a time bin or frequency for the transmission, for example. So indeed, those things will also matter for the practical implementation of these things beyond the lab. Or if you want to do hybrid things where you connect two different hardwares, it might be that one works well with time bin, for example, defect centers. The other one with polarization. Then you need to convert between these two. All right. I think that was the end of emission-based. And as I said, I'm going to skip the repeater, which is the next thing, and instead dive into scattering-based schemes here, which is a different beast. We're going to look a bit more into James Cummings Hamiltonian, derive the reflection transmission things that hopefully give you the toolbox to make new entanglement schemes and mix and match different things yourself. And we're going to do that instead of talking repeaters. That being said, I'm happy to talk about repeaters if there's time at the end and whatnot, but yeah, I won't be covering it in the lecture. Okay. Because I think now at 11 there's a break, right, of 30 minutes. So let's take that break now. Thanks.